Okay, high states. So blazars are divided into two categories. So BLUC with low high energy bump, blue curve, and magenta curve. These are BLUC objects, and high energy bump, for instance, black curve. These are FSRQ, so flat spectrum radio quasars. And so the origin of blazar emission, it's debated subject. So for low energy bump, there is a consensus that this is synchrotron emission of high energy electrons which are radiating in the extended jet, plus contribution of Hot galaxy in the optical domain. And for the origin of the high energy bump, this is debated, and there are two classes of models: leptonic models and hadronic models. So leptonic models presume that the emission originates from the nature of the emission is inverse Compton process, either upscattering of the synchrotron photons from the low energy bump by the same high energy electrons, or upscattering of external photon fields, which are not originating from the gamma ray emitting zone. For instance, BLR, broadline region photons, or accretion disk. And hadronic models, they presume completely different nature. So for instance, proton synchrotron or P gamma PP interactions. And this is an example of it. So why do we want to study blazars at all? Why is it interesting? So nature of flaring activity is poorly known, as I mentioned. Then we're not sure about the matter content in the jets. So we want to study jets, which we cannot, unfortunately, we cannot reproduce them in the laboratories. So these are really extreme and spectacular phenomena, and we want to understand their physics better. So the matter content, so leptonic or hadronic composition, then what is the location, what is the precise location and geometry of the very high energy gamma ray production site, different acceleration mechanisms operating in jets, and as I mentioned, nature of flares. So very briefly about possible mechanisms that can drive blazar flares. So there are two broad classes of models. So the activity can originate from the very close to the central engine. For instance, a crossing of a red giant star close to the black hole, tidally disrupting it and accelerating particles, or pulsar-like acceleration in the vacuum gaps near the black hole, or jet precession. Or it can be originating in the extended jet, so far further from the black hole. It can be, for instance, a geometrical effect, like in the case of jet bending, where you have a decreased angle with the line of sight. So you get Doppler boosted emission and an increase of flux. Or it can be microphysics of the emitting zone. And I was focusing on specifically this type of model. So I was working on transient turbulence, which is spontaneously arising around the emitting zone. So, and in order to understand the nature of flares, of course, we need observational data. So now I'm going to present the analysis of Hess data, which I did. It was one of the sub-projects. So Hess experiment is located in Namibia, and it's the largest ICT system on Earth at the moment. And so the source of interest for me was 3C279. So I was analyzing two bright flares of this source, which happened in January and June 2018. So this is flat spectrum radio quasars. So high energy bump is so high energy bump, and the redshift is also quite significant. So it's 0.5, and the high energy bump is located around 1 GeV. And so in 2018, Fermi issued 3 alerts to Hess, and so there were 3 flares observed by Hess in 2018. So January, February, and June. So, and my contribution, so I was a member of a dedicated task force to analyze the data collected during these 3 flaring states. And my contribution to this task force was an analysis of pre-very high energy flare data. So this band, so before the secondary flare in Fermi. So what was the properties of the spectral properties before the actual outburst. And also I was analyzing data during the very peak of the June 2018 flare. So for the January flare, so I selected 3 days data, and I used CT5 data, which is the largest Cherenkov telescope in Hess array. And I use CT5 data because it's the only telescope having enough size to collect faint Cherenkov light from, which is the only telescope from Hess array sensitive in around 10 GeV energy band. So for CT1 to 4, there wouldn't be any detection. So unfortunately, in January, there was very marginal, if we even can call it detection. So at 3 sigma level, which is a rather weak indication for gamma ray signal. So you can see the excess map, the left panel. So there is very, weak indication for signal, and significance map is showing the same. And significance distribution here in the tail, you can see something around 3 sigma. There is a signal, but we don't claim detection in this case, which is not the case for the June flare. So for the June flare, so the data during the peak was collected without a wobble, so there was no background measurement. And for the subsequent nights, there was a wobble measurement. So, and I decided to take this night to try explore a different analysis approach. And so I used a background technique, which is different from the one used for January flare, which was multiple off. So, and this is a non-standard technique. So I found, using dedicated tool in the Hess analysis software, I found an off run, which is matching the on run collected during the peak of the flare. And we detect the source during the peak of the flare at 11 sigma, which is clear detection. And using the data, I computed the spectrum of the source during the flare peak above 60 GeV, which is shown here. And so it extends up to few TeV, which is a remarkable result, I think. And the spectral index is around 3.4 during the peak. And we can judge that this is harder than during the decay. So the task force, other members of task force measured it during the decay. So it's a very preliminary result, but it turns out to be around 5, which is much softer. So, and in Fermi, about 100 MeV, we can see that there was also spectral hardening. So the index, it actually hardened from 2.5 to 2, and then it again returned back to around 2.5, which was also done by the task force. So we can see that in the gamma ray range, there was a noticeable spectral hardening, which we may interpret as an indication of particle acceleration in the source during the flare. So, and I also computed the peak gamma ray flux. So I published these results in a proceedings of 36th International ICRC conference, together with other members of the task force in 2019. Then I would like to present the core of my work, so physical modeling of flares. So in parallel to analysis of Hess data, I developed a versatile code to model blazar flares. And unfortunately, 3C279 data was the data set was not complete. So it was not really easy to perform sensitive physical modeling because there were not so much observational constraints. So I decided to select another flare of another object for my modeling effort. So now I would like to present a general framework needed to model blazar flares within kinetic approach. So we made few really fundamental assumptions. So we assume that the gamma ray emission of blazar originates from a compact region of plasma, so which is called Blob. So this is Blob in jet model. And there are other types of models. So, but we focus on this particular view. So we assume purely leptonic blob filled with electrons and positrons and no cold component. So all the particles which are residing in the blob are relativistic. So there are few physical processes which are happening in the blob. So particles are injected in the emitting region. They can undergo acceleration. Fermi 1 by shock or Fermi 2 by turbulence. They escape, they leak out of the emitting region, and the particles emit synchrotron emission, so SSC emission, and they undergo synchrotron and inverse Compton cooling. So, and this is the fundamental equation which I was solving numerically. So this term is showing the cooling effect. This is Fermi 1 acceleration, Fermi 2 acceleration due to systematic energy gain, the Fermi 2 contribution to diffusion in the momentum space, the leak term, escape of particles, and injection spectrum. And this equation basically represents the continuity equation in the phase space and dictates us the evolution, the time evolution of the electron spectrum in the emitting zone in time. So now this was the first level. The second level is computation of the emission. So what does this particle population is emitting? So we assume SSE emission, so leptonic view, and synchrotron emission is creating the low energy bump. So and it's self-absorbed at low frequencies, and SSE emission, so for high energy component. So the low energy synchrotron photon is upscattered is interacting with the high energy electron and is upscattered to high energies. And also this emission at high energies above, say, 100 GeV suffers from absorption on extragalactic background light, which is ubiquitous radiation field in the universe. And it shows two components, so infrared and optical. And when very high energy gamma ray with the energy of a few TeV interacts with this photon, with the soft photon, when it collides, it creates electron-positron pair. And you have attenuation of the very high energy flux, and this plot shows you this effect. So depending on the redshift and energy, so typically about 1 TeV, especially with redshift, you are heavily absorbed. And we transform the observations, we transform the emission to the observer's frame as the blob is moving relativistically along the jet with the high Doppler factor around 1030. So you get Doppler boost of the frequency, but it also suffers, the photon also suffers from cosmological redshift. And you've got headlight beaming effect expressed with this delta Q factor. And so the emission is amplified. And so we compute the SED at each electron spectrum at each time step. And the light curves are obtained by integration of the SEDs in energy range of interest. So a few additional assumptions in our model. So the magnetic field, we assume that this is homogeneous and is not changing in time. The turbulence, so the turbulence is described with the power spectrum, typically power law in the wave number, which is with the index Q. And we assume hard sphere approximation with Q equal to 2. And this means that the Fermi 2 time scale will be energy independent. The same for escape time scale, as well as we assume that it is energy independent even without turbulence. And we assume that the parameters of the emitting region are not changing during the evolution. So now I'm presenting you my code, the time-dependent SSE code I developed for computation of the variable emission of lasers during flares. So it's named Emblem, which is evolutionary modeling of blob emission. So the architecture of the code, so the skeleton goes like this: the input parameters, which I will cover in the next slide. So you specify the input parameters, and then you compute the electron spectrum using Chang and Cooper numerical scheme. So you get the electron spectrum evolution on the time grid, and it serves as an input for SED computation. And then you get the SED evolution in time. And this is all written down to output files, and then you generate light curves by integration of the time-dependent emission. So the input parameters, so there are physical parameters of the blob, like its magnetic field radius, Doppler factor, evolution parameters like time scales of injection, escape. Then you can specify explicitly the injection function. So it can be power law or with the cutoff, or it can be arbitrary time-dependent function. Also time scales of acceleration. And the peculiarity of my code is that you have really freedom and flexibility to control the acceleration process. And this is the feature. So you can activate the acceleration process only for a specific duration of time, or you can arbitrarily parameterize this acceleration process, and I will discuss it in more detail a bit afterwards. So then you specify EBL model name and redshift of the source. So in my work, I focused on the brightest very high energy flare of Markarian 41, which reached 27 prob. above 1 TeV, and it happened in February 2010. And it's very rare and quite exceptional time coverage across the entire electromagnetic spectrum, because you can see that the light curves, the light curves available, you have measurements from radio to very high energy gamma rays through X-rays, which is really remarkable. Also, there are spectral measurements available, but I will come to that. So we make a strong assumption in our model to model flares. So we assume that the flare is only a moderate perturbation of the quiescent state, so that the physical parameters of the emitting region is not changing during the evolution. So like the emitting region is not compressing and magnetic field is not varying. And what justifies this assumption? So for instance, you can see that for most light curves, the post-flare flux is consistent more or less with the pre-flare, so that your flux returns back to the initial value. So that's why we treat it as a perturbation. And so the aim of our work is connect the steady state emission, so the quiescent level of the flux, to this high state one, using a coherent description. So first we need to model the baseline, the quiescent state of the source. So we assume a physical scenario in which, so this blob and jet view, in which the electrons are injected into the emitting region and they undergo cooling and escape. And these processes, gain and loss processes, they compete, and you got steady state, which is established. And we feed the low state measurements. So this is the sketch representing the low state model, and this is the upstream shock. So we assume that the particles are injected into the blob from the upstream shock, so the power law with exponential cutoff. And so we fit the low state measurement performed by these authors. Sorry for clicking. So the multi-wavelength data set is spanning from radio frequencies to gamma rays, and this was obtained during a multi-wavelength campaign on the source when it was showing low flux level in 2009. And it's averaged over 4 months. So the green curve shows the model, our model. And as you can see, it represents the data set quite well, with except for the radio data where we underestimate the flux, but we assign this discrepancy to the contribution of the extended jet, which we don't include in our model. So, and the injections function, so we have a power law with -2.2 slope, which is fully consistent with initial hypothesis about the relativistic shock injecting particles. So now we start to generate flares, and the simplest scenario which we can imagine is just perturbation of the emitting region with shock or turbulence. So we assume transient acceleration processes. And then, as we will see, these models do not provide a satisfactory description of the flare data set, and we will gradually complexify the models, adding meaningful parameters step by step. And so either an emitting zone is crossing a shock, or the shock is perturbed and you have turbulence downstream. And so it's a very simple model. And so you've got only 2 parameters which control the flare. So this is working like this. So what I was doing is just using these kind of control panels. So you specify the time scale of Fermi 1 or Fermi 2 acceleration. Then you start your shock or turbulence acceleration. You wait for a certain amount of time, and you stop your acceleration process. And the particles are reaccelerated, and you got more high energy particles, spectral hardening, and you can get a flare. So, but unfortunately, this model doesn't work. So the simplest scenario cannot adequately describe even 2 observational constraints. So the blue point shows the X-ray measurements around the peak of the flare, and the magenta or violet points show the peak optical flux. And the black curve is the low state SED model. So you can see the increase in optics is very modest, and increase in in X-rays is quite significant, factor of 5, 6. So while the one-zone models describe the X-rays, they completely overproduce the optical emission by a factor of 3. So we conclude that this model is too simplistic to describe the flare. Already we rule it out with 2 observational constraints, and that's Fine. So we proceed to complexify our model, and we assume two-zone configuration, which we justify by the fact that we want to dilute the optical variability. So we assume maybe the optical emission is dominated by one component and the X-ray flare is created in another component. So we assume a two-zone configuration in which the green is the steady blob emitting the quiescent flux, and the blue is the transient turbulent zone, which is existing for finite amount of time, and these regions interact. So there are interchange of flows of particles, and this region can be either radiative or non-radiative. So I explored both. So the non-radiative model is actually not describing data set well, while the radiative gives a satisfactory description. So, and we assume a limiting case in which the emission the particle flux from the turbulent region, represented by yellow arrows, is negligible compared to the upstream shock. So, and so what's happening in this scenario? So the particles which are escaping the emitting region, the steady blob, the pink arrows, so they're injected into the turbulent region, and the turbulent region is re-accelerating these particles. So you have spectral hardening and you have a flare. So quickly about the mechanisms, how we can actually excite the turbulence in the jet. So it can be various hydrodynamical instabilities like Kelvin-Helmholtz or Rayleigh-Taylor rotationally induced, a magnetic reconduction due to various, like for instance, plasma beam instability, or stanting shock, which is amplifying weak turbulence, or the emitting zone can cross a cloud of gas, or other plasma instabilities can be at work. So, but in our model, we don't really focus on the nature of the turbulence, but rather try to describe the emission within the kinetic approach. So the approach for the modeling was the following. We in fact have quite a few constraints on the parameters of the turbulent region. Like its injection spectrum is defined by what is the blob ejecting. So in the solid angle enclosing the turbulent region, then we assume that the transient turbulent region is actually co-moving with the blob. So it's the same Doppler factor. And the turbulence, we assume that the turbulence is injected with a linearly increasing and decreasing rate. And we treat the evolution of turbulence self-consistently, so not just switching on and switching off, but a bit more complex approach. So the Fermi 2 time scale, the time scale of acceleration, it depends on the magnetic field energy, the fluctuations of the magnetic field, depending on time, which is this triangular shape. And it also depends on the Alvan speed, which is time dependent because it depends on the electron energy density, which in turn depends on the electron spectrum, which is varying in time. And the escape during the turbulence is actually slower than during the low state, because the particles have to undergo diffusion through the turbulent plasma. And the escape time scale is linked to Fermi 2 time scale and the Alvan speed. And this is our treatment of turbulence. And then we also take into account Fermi 2, we also take into account cross scattering between the two emitting regions because they are in close contact. So, and we find that the contribution, the external compton, so scattering of quiescent emission of the electrons in the turbulent zone provides important contribution, and we take it into account. And so we fit the parameters, so we adjust parameters to represent the data set well. So this is our final solution. So these are the parameters of the turbulent zone. Magnetic field is similar to the one in the emitting, in the steady emitting region. Size is order of magnitude smaller. And this is the time evolution of the electron spectrum, which is proceeding from violet curves to the red ones. So you can clearly see the spectral hardening. This is around the peak. And then the spectral softening and also high energy cutoff is extending. And these are the light curves. So we managed to reproduce the variability pattern quite well, starting from optical through the X-ray measurements and up to Fermi and the very high energy gamma rays, with the only discrepancy in optical, or the variability amplitude is more or less correct, while there is an offset of around 10%. Which might be due to different factors, like our model may be incomplete, might not treat external contribution in the optical band, or the data might be suffer from inaccurate whole galaxy subtraction. Also, we don't treat the secondary flare, which is visible in X-ray, which might arise due to another, for instance, another injection of turbulence. Then I would like to show you the evolution, the time-dependent evolution of SED during the spectral energy distribution during the flare. So this is the compilation of all curves with a time step of around half a day, and with various spectral measurements imposed. And now let's go step by step. So this is the very beginning of the flare. Then it's evolving. So there is hardening and increasing of the whole SED shifts. And this is around the peak of the flare in Fermi and in X-rays. So you can see we reproduce quite well optical X-ray measurements, but slightly underestimate Fermi, Fermi band here. Then, okay, it's, the optical is still well fit. Then this is 1 day after the peak of the flare. And this is Veritas measurements taken at this date. And so we reproduce Veritas measurements quite accurately up to a few TeV, so up to like 4 or 5 TeV, but then we see a discrepancy. But it should be noted that these points actually were never published in a full paper, but only in a proceeding. So they might suffer from systematics, but it also might be that our model, okay, our model is imperfect. And then this curve shows the SED more or less during the flare decay, well, during the flare decay. And the data here is Hess time average measurements from MGD 45 to 47. And so the next time step, so 46.1 is right in between. So, and we represent quite well the Hess time average spectrum during the flare decay. And so then the flare is completely, well, it dies off, so it's fading. So now let's discuss our model a bit. So, so Blazar flux shows some often log normal distribution. And we propose that this might be due to turbulence in the jet. And so various stochastic processes, they induce noises. And the noises, how the amplitude of the variability is distributed over the time scale is described with PSD, power spectral density, typically a power law in inverse variability time scale. So if it's 2, then it will be red noise, and 1 is pink noise. So for Markarian 4-1, in the low state, the measurements of the PSD show slope -1, which is pink. And during the flare, the noise was seen to be redder. So a Veritas collaboration measured it to be -1.75. And we propose that this might be due to the slowly varying shock acceleration in the low state with superimposed transient Fermi-2 acceleration in hard sphere approximation, justifying our choice of hard sphere approximation. So these results were published in a number of publications, so in conference proceedings, and they were submitted to monthly notices a month ago. So I'm still waiting for the answers from the referee to arrive soon. And also the results were presented at various conferences and workshops. So now I am very eager to apply my code to CTA data, but we don't have yet CTA data. That's the problem. So I decided to get involved in CTA as early as possible and contribute to its preparation. And so my work was dedicated to gamma ray Cherenkov telescope. I will discuss it very soon. So CTA is, as you know, it will feature 3 types of telescopes, and it will be composed of LSTs, MSTs, large size telescopes, small size telescopes, and medium size telescopes. And its energy range will be substantially extended up to 300 TeV, and the sensitivity will be growing by a factor of 10. So when I was working on gamma ray Cherenkov telescope, which is one of the 3 designs proposed to CTA for small size telescopes, so the telescopes which will reach the very high energies. So 3 designs, so this is GCT, France and UK, Astri by mainly Italy, and SST1M, Switzerland, Poland, and others. And so GCT and Astri are dual mirror telescopes, while SST1M is a single dish. And so I was working on GCT, which is based on Schwarzschild-Coudet optical design, which is known for its quality by correct. So the advantage of this design is correcting optical aberrations. And also it's a first telescope employing Schwarzschild-Coudet optical design, contrary to conventional single dish or devious cotton designs, and it's very well adapted to fine pixel silicon PM cameras. And so the M1, so this is the M1, which is primary mirror. It's composed of 6 hexagonal petals or segments, and this is M2, which is monolithic. And these mirrors are metallic, and the overall design of GCT allows quite lightweight structure and a lightweight camera. And so prototype to validate the design. So the prototype was constructed at Meudon site of Paris Observatory. And my goal was to characterize the optical performance of GCT and the prototype using a robust ray tracing code. So here you can see the prototype installed on the Paris Observatory site. So this is M1 composed of 6 actually circular petals, of which up to recently 2 were real mirrors and other 4 were dummies. This is the secondary mirror. And as you can see, so this is clearly 2020, and you can see that this is summer. And this was in August. The picture was taken in August 2020 during installation of new mirrors with much higher polishing quality. So I simulated the current, not the current, but the previous prototype configuration before the mirror installation. So which featured 2 round segments. And this is the robust computational model. And so I deduced, and also the same model for GCT, which features 6 hexagonal petals. So when I did using the ray tracing code, I deduced the ideal optical performance of both prototype and GCT. So this is the curves for GCT showing effective area versus off-axis angle. 80% containment radius for ideal PSF, which is around 1.5 arc minutes. And this is the spot progression in ideal focal plane. And so I also estimated the shadowing effect induced by masked trusses camera body, so obscuring elements between M1 and M2. And this plot shows you the effective area of gamma ray Cherenkov telescope with obscuring elements, the green dots, and without them, so higher effective area. And so shadowing on axis is around 12%, while at the edge of the field of view, it reaches almost 20%. So then I was involved in modeling of PSF of the prototype. So the situation in 2018 was the following. So there were these 2 circular segments with rather average surface polishing quality. The mirrors were manufactured in 2014. And so we were studying the PSF of the prototype, and observations were carried out in autumn 2018 and via observations of bright stars. And the PSF structure appeared to be double Gaussian. So you can see it on this plot. So it does not fit well with one single Gaussian, but rather with the sum of 2 Gaussians, a narrow one and a wide one with these values of D80, 80% containment diameter. And so my goal was to model the PSF, and our assumption about why we observe the structure is the micro roughness of the primary and the secondary mirror. So, and to verify that, I simulated in the following way. So a fraction of, so I assume that so there is a following picture. So a fraction of rays falling on the mirror are scattered, and another fraction, y, is diffused in an angle theta diff, and this fraction is controlled by the micro roughness parameter. And so using these scatterings between M1 and M2 and reflections, so 4 components arise. So scattering purely on M1, diffuse specular, scattering only on the secondary, specular diffuse, scattering on the both, which is diffuse diffuse, and reflection from the two mirrors, which is specular specular. And then running a bit ahead, so this plot is showing these four components to the final modeling. And so the white component is dominated by scattering on the one and scattering on the both, while the narrow component is dominated by the specular specular. And so the idea was to simulate the PSF in a way that the simulated profile, the simulated profile of the PSF is described by the same double Gaussian than the actual real data. So these parameters should match. And also the ratio of the areas below these Gaussians. So we reproduce well the ratio of the areas and the width of the wide component, while we slightly underestimate the width of the narrow one, which is might be due to omitting, we don't include the misalignment errors, but overall we reproduce the PSF quite well. And so it can be explained, really can be explained by the micro roughness of mirrors. So this plot shows you so green curve is the simulated data, matching well the observed one. So it's explained by the same, it is fit by the same double Gaussian structure with the width of this component is 14.6 millimeters as in data. So for the mirrors manufactured in 2014, we conclude that the micro roughness is around 40 nanometers. This is typical surface irregularity size, which is very well in agreement with actual laboratory measurements performed with profilometer. And the inferred diffusion angle is around 4.3 arc minutes. So, and we made predictions with the optimized mirrors. So what PSF can be achieved with much better mirrors, with polishing, which is fairly easily achievable with current technology of around 7 nanometers. And it can be even better, but that's already good enough. So I extrapolated these results using PSF modeling, and I concluded that we can achieve PSF of 3 millimeters. And it has to be validated on Sky, and there were measurements carried out in September this year, and ongoing tests on Sky look quite promising, and it appears that 3 millimeters can be really achieved. It seems to be achievable, and this fully proves the potential of the GCT and Schwarzschild-Coude design in Cherenkov astronomy. So these results were published in proceedings of ICRC and SPIE and presented at various talks also. And I'm close to the end of this of my defense. So I would like to summarize. So I was working actually on all three facets of astrophysics. So on the theory side, modeling side, so I developed the time-dependent code to model blazar flares, and I applied this code to the brightest flare of Markarian 41, and developed a novel physical scenario to describe the behavior of the source during this spectacular flare. I was also working on observations and data analysis. So I was involved in HESS. I was observing on the HESS site in July 2018 for 1 month in Namibia. And I was contributing to the task force on analysis of 3C279 flares. And I also worked, I'm lucky, I had a chance to work also on instrumentation side. So, and I characterized optical performance of gamma ray Cherenkov telescope for CTA. And perspectives. So what are my plans for the future? Okay, first will be short vacation, but after that, I plan to extend my code to the case of flat spectrum radio quasars. So to treat the external photon fields. And I already have in mind a flare to model, so 1510. And preliminary analysis shows that it might be even fit without the external component, but that we will see. And of course, many more flares of many more blazars. And there is a lot of interesting variabilities to explore at different time scales, not only 1 day, but also 1 minute, 1 week, and up to 1 year. Then I'm planning also to perform statistical studies on different sources and contribute to CTA, of course. I plan to stay in CTA. My plan is to contribute to the task force on AGN flare modeling. So it's an endeavor to understand what science can CTA do with flares. So the potential of CTA to unveil the physical processes during the flaring activity. So as we will have much higher quality data, and in the far perspective, to apply my code to future CTA data, already extended code, and so many, and to explore many new interesting behaviors in blazars using that code. And I would like to conclude my thesis defense with a quote by Richard Feynman. So I would rather have questions that can be answered than answers that can be questioned. Thank you for your attention.
Thank you. It's time for questions. So I think we will start with the two rapporteurs. So Paula, are you available? We'll start with you.
Hello, yes. So thank you for your nice talk, Anton. Well done for getting all that in 45 minutes. That was quite impressive. I enjoyed reading your thesis. It's very interesting, and you did some really great work in terms of the modeling. I'm by far from an expert in the modeling aspect of what we do, but that was very impressive and very ambitious. So I wanted to start a little bit by talking about some of the analysis that you did. And maybe, are you able to go back to slide 19 for me?
Yes, sure. Yes.
Okay, that's great. So a couple of things I wanted to ask you. You mentioned that you had to find an off run
Exactly.
in order to find your signal, if you like. Can you just explain to us how you go about finding an off run that would work with your on data?
Yes, sure. So this off run was taken not really not even close to June 2018. So the idea is to find a background measurement. So cosmic ray, residual cosmic ray background measurement that is matching the observational conditions, which were during the 1st June 2018. So there is a dedicated tool in the model plus analysis. So the analysis tools of HESS, which I was using. So and the tool searches for off runs matching the on runs based on manually specified criteria. So the conditions were the following. So the zenith angle should be not deviating more than 5 degrees. The same for azimuth, and also the number of telescopes should match. So only 55, and also something else. I don't clearly remember all of but the most important is really the zenith angle is really crucial, because you have strong dependence of the cosmic ray background on the zenith angle. So this how I found the off run. So there were 2 runs actually, and for for 2 runs I found 2 off runs matching, so paired them and analyzed like alternating sequence.
Okay.
Does it answer the question?
Yeah, it does. Do you have to worry about atmospheric conditions as well?
Yeah, that's also quite important. I agree. There was nothing, so I think it was delegated to you to check. I mean, to me, to check whether the atmospheric conditions were the same, like no clouds or. Yeah, I agree. I didn't really check for that, but I agree that this is important.
Yeah, the clouds are usually quite easy to spot.
As they attenuate the training of light. So
general attenuation is much harder. Yeah. Second question on this slide, actually, looking at the spectrum that you have, it's very much a power law spectrum, isn't it?
It is,
which
yeah.
for an object with a redshift of just over half is quite impressive. Can you say anything about the extragalactic background light from this measurement?
Yeah, I agree that it should be heavily absorbed, say above 200. I think for the redshift 0.5, the tau equal to 1, the opacity of 1 is achieved at 200 GeV. in a like moderate EBL model. So yeah, for me, this is also a remarkable result. So that means that the opacity is somehow overestimated. And but I agree that this is okay. I have to admit this is a preliminary result. We didn't cross-check it with actually other analysis chain hub. There should be cross-check for this night, and if I remember well, that was not yet done. So that's on the side of other task force of the other members of the task force. So these results are we cannot yet publish them without the full cross-check. So that remains preliminary.
Yeah. Okay. Well, let's see what HAP produces, but it'd be very interesting, I think, if it also looks like a power law. Yeah. Okay. So I didn't want to go too much into all the details of your simulation code, because I'm going to leave that to Marcus, because I think he's much more expert than I am. But I did want to ask you a couple of things about the way that you approached it. So my first question was to ask you, why did you particularly choose the Blob and Jet model as opposed to another multi-zone SSC type model?
Yeah, mostly because we in our laboratory we already have codes which were based on this structure, Blob and Jet. So, and it was natural way. So my intention was to explore this particular model. So, and I agree it would be interesting to. So 3 years of PhD is really too short to explore many more different models. So, and possibly I should have included it into perspectives. But in my thesis, I really focused only on this view.
No, for sure. This makes perfect sense, right? You have to start somewhere.
So you have to make a choice at some point. Yeah.
Yeah, exactly. And the other question I was going to ask you, actually, it takes a lot of effort to write your own code. And there are other codes out there, and there are lots of them. Why did you choose to write your own code? And I guess maybe I'm asking, what's special about your code that wasn't in the other codes?
Yeah, so what's special is the particular feature is treatment of acceleration process. So we, as you can see, we treat Fermi 1 and Fermi 2, and it's so the particular, first of all, is the general assumption about the perturbation. So we treat flares as a perturbative effect, not, for instance, other authors assume that this is a purely stochastic effect. So you cannot apply the same model. So in my model, this is purely, so you have in the low state, you don't have these Fermi 2, Fermi 1 terms, and then you suddenly switch them on when you have acceleration. So the treatment of turbulence, as you can see, is also quite it's more complex. So even more complex than just enabling and disabling these terms. So these coefficients, they are actually time dependent, and they may be also energy dependent in the case of other types of turbulence. So my code is really, the particular feature is this detailed, self-consistent way of treatment of a turbulent reacceleration. So I plan to also to extend my code to include different turbulent spectra like Kolmogorov or Krajnan.
Yeah. Okay. So now I want to jump completely to something that you know is dear to my heart, which is the GCT. So maybe we go to slide 56, I guess.
All right.
I told you there would be a jump.
Yeah, no worries. So I'm almost there. Yes.
I'm also aware that I shouldn't go on forever. Okay. So first of all, what's the normal, if you like, design for a Cherenkov telescope? What are the features of the Davis-Cotton optical design?
Yeah, so up to now in Cherenkov astronomy, I think that was the only design used. So yeah, so I think that was, and so for GCT, this is a particular curvature. The mirror has a particular curvature, like polynomial shape, which is not the case for Davis-Cotton. I think Davis-Cotton is just parabolic.
It's spherical, actually.
Spherical. Ah, yes.
Even simpler. Even simpler.
Five.
Yeah.
Yes, it's CT5, which is parabolic. Yes.
Yeah.
Yeah. Spherical.
Okay.
Yeah, but they don't actually correct aberrations well. So, which is the case for Schwarzschild-Cuda.
Yes. Why does that give you a particular problem for the small size telescopes of CTA?
Sorry, can you rephrase?
So let me think about it. So the medium sized telescopes, for example, of CTA,
Yes.
will be in general Davis Cotton design. We know our American colleagues have a Schwarzschild-Cuda design, but at least at the beginning, the medium sized telescopes will be Schwarzschild-Cuda. The large size telescopes are a kind of modified. Sorry, the large size telescopes are kind of modified Davis Cotton. Medium sized telescopes will be mostly Davis Cotton. Why did we want a dual mirror design, particularly for the small size telescopes? What's important about it?
So yeah, it's easier maintenance and different operational modes. So as we want to, these telescopes, they reach the highest energies, so up to hundreds of TeV.
Right.
So, and we want different operational modes. We want lightweight structure camera. We want and we want we want easy, quick maintenance, because these telescopes are small. So even you don't need special equipment to access camera or other details. So it can be quickly replaced if needed or corrected. So it's much more flexibility.
There's also something else. What's the field of view of this telescope?
Yeah, it's around say half of the field of view for 4.5 degrees. So 4.5 degrees.
Yeah. Do you know what the field of view is for, say, medium-sized telescope?
I don't think it's much different.
It's only about half of, in fact, a bit less of the field of view than the small-sized telescopes.
Okay.
Right. So can you think why we might want a big field of view for the small-sized telescopes?
Well, you always want a big field of view to have, to analyze, to see several targets at the same time.
I think it's more that the highest energy events are quite rare, and so the bigger your field of view, the better your chance of detecting them, and the more spaced out you can have your many telescopes. So we have to have many telescopes. So the bigger our field of view, the more we can space them out. So we need not quite as many as we would have done otherwise. And that's, I think, is a major driving factor for these dual mirror designs, because as you rightly said, the Davis Cotton suffers from really poor aberrations when you get to big fields of view, whereas these telescopes don't. And as you also rightly said in your talk, we can use the small pixels because we have, in effect, a small plate scale. Whereas if you want to build a big field of view with a traditional Davis Cotton telescope, your camera becomes completely dominant. It's enormous and costs a fortune. So you probably don't want to do that. Right?
I see. Yeah, so 3 millimeter PSF, which almost proved to be reachable. So it's more or less compatible with this fine pixel silicon PM camera. They have similar size of pixels, so it's a perfect fit.
It's a really good fit. And I was going to ask you one very last question before I stop asking you questions, which is, why don't we make mirrors like our optical friends? Optical astronomers would never make mirrors like we make them. What are the particular problems we have?
I mean, why do we have segmented mirrors?
Why segmented? Why solid aluminium? Why don't we just make them like glass and like normal astronomers do? Why don't we do that?
Yeah, good question. Yeah. So yeah, they are done. The mirrors are metallic because, first of all, like it's very difficult to polish very well glass mirrors, and it's first of all, it's difficult technologically, and second, it's much more expensive. And then the segmented mirrors are because you need to achieve a particular shape of the mirror, which is again very costly and very difficult to if the mirror would be monolithic. So for 4-meter mirrors, you have very big chances that you will not achieve as high quality, and also I mean, at some point there also should, like, the mirror is heavy, so you can have local distortions, like surface, like you can feel the gravity. So your mirror will be, you will have to, well, the problem will be with monolithic mirror also that you cannot control locally. So you have actuators which are attached at the back of each segment, so you can really adapt your shape and your well, focus. If you're out of focus, you can quickly adapt for that. And this is impossible with the I mean, there is adaptive optics, but this is a different story. So you cannot really control easily the monolithic mirrors. So they're more difficult to manufacture and more difficult to operate.
Yeah, very true. And also most optical telescopes are not tuned to have really good reflectance in the blue/ultraviolet.
Yeah.
Right. And so you can't have rear coated glass mirrors because you absorb most of the blue and ultraviolet, which is not ideal. Okay, I will stop now lest the chair do terrible things to me. Thank you, Anton, and
Thanks
well
for your
done.
questions.
Okay.
Yes.
Thank you, Paula. Gilles?
Yes, hello, Anton. So first, I wanted to congratulate you for your thesis and your manuscript. It was very.
Thank you very much.
I was very happy to read it, and it was a very good coverage of the field because you address so many problems going from instrumentation to data analysis to modeling, and it's impressive how well you mastered all that, and you described it in your manuscript. So I enjoyed a lot the reading. This said, okay, I got questions, of course, and I raised some questions in my report, and then we had some change about them. And so maybe I will be back and maybe ask other questions too. So as I said in my report, I was a little bit puzzled by the fact that you start with an original model, which is the Blob injet model. And in the Blob injet, the conventional wisdom is that there is a surrounding jet that is responsible for the steady emission, and you have an active blob that is producing all the flaring behavior. And at the end of your work, you end with a different view, that is the blob is more responsible for the quiescent emission, and you have another active zone which is not the blob, but which is surrounding the blob. So I had question about the physical justification of this view, and especially if you compare with radio long wavelength data. You said it's probably due to the long range jet, but where is the jet in your model? It's not really visible where the jet will radiate. So maybe if you go to the slide number 35, that's just a way of asking this question. Yeah. Just take this picture and just imagine the opposite. That is what you call the blob is actually the outer region, and what is the active region is the inner region. Would it change a lot your model, or is it totally excluded? Because it's just a question of where you put the regions. But if what you call the blob would be the outer jet, and the active region would be the inner region, is it possible to imagine that, or totally impossible?
Okay, I understood your question. I believe that that won't change too much if I just swap them, but clearly the parameter, I mean, I need to adjust the parameters of the turbulent region. So now we can imagine a blob is like a torus, which is surrounding the turbulent region, and turbulent region is transient zone in between. So, but now what's happening? So let me think. So now it will be that the turbulent region is injected. You see, so I treat the exchange of particles and the emissions, cross scatterings. So now the turbulent region will provide both particles and emission upscattering the electron. So I believe, well, I can simulate this configuration as well, but I need to really verify what's happening with the, you see with the fluxes shown in yellow.
Okay.
So, but I think it, I cannot tell you whether it will fit this flare, but it's definitely possible to simulate that.
Okay, so there is no obvious.
Take into
answer.
account the flux.
Okay, I had a question too with Lorentz factors, because you assume that it's the same Lorentz factor for the blob and for the active region. Is it if there a real strong constraint on the Lorentz factor of for the quiescent emission? Because usually the constraints are deduced from the flare parameters, flare observations. But do you think this quiescent state has a strong constraint on Lorentz factor or Doppler factor?
So in my case, so quiescent emission, so it's around 30. The Doppler factor of the blob is around 30, and that's there is a lower limit, which is by requirement of escape of gamma rays due to gamma production.
Yes, my question is, does this limit apply to the quiescent state too? Because for the quiescent state, the limit is less stringent.
Yeah. Well, it should be several tenths. It can be very low, like it can be below 10, I think, and higher than 50, 60, that would be, yeah, that would be quite too high, in my opinion. But the constraint is the positions of the peaks, actually. So it's okay. It's the whole kind of there is okay. This peak is actually more or less in Klein-Nishina regime, so you cannot really push it further. But the synchrotron bump, so it is quite sensitive to the Doppler factor. So at some point you have competition between cooling and losses and injection. So injection, escape, and cooling, they compete. So this is defining more or less the position of this bump and in the source frame and in the observer frame. So it's boosted by Doppler factor. So and these.
How did you come to this 29 value, for instance?
Sorry, can you repeat?
How did you arrive to this 29, the value of 29?
I was varying. I was varying parameters in like Doppler factor in the range of 10 to 30. And I have to, since you asked, so there was a stationary modeling done, instantaneous modeling done by these authors, which present the compilation of the multi-wavelength data set. And they performed stationary modeling SSC, and they deduced parameters, so stationary parameters, and they had very similar Doppler factor. I think it was, yeah, 20, 21 or 20, in the range between 20 and 30. So, and in various theoretical works, you can actually find that these parameters, they can be quite well constrained from the peak positions and also from the ratio SSC component to the synchrotron. So it is typically okay, but I have to also admit that we're not aiming to precisely measure physical parameters, so it's more like indicative result, and the result overall is more qualitative. So like Doppler factor around 29, but it can be also 25. In principle, you can, because you see it's not clear exactly where is the peak. It is from around 200 EV to around 600 EV. You can adapt, but there is a certain range. So this parameter, all these parameters, they are actually more. They're in it's not like very precise values, but it's more some narrow range around them, plus minus a few. So 25, say 32, more or less. But it's a good. I agree that it would be good to explore really the domain in which we can still fit the data. So because also we can see error bars. So clearly.
Yes, of course. Okay.
Did I transfer?
Yes, more or less, but as you said, I don't think it's really well constrained from this kind of observation. You have to put other constraints like gamma ray opacity, things like that. Okay. I had a question about in the cooling process. You said you include synchrotron on inverse Compton cooling. You always took isotropic approximation for the inverse Compton cooling. Is it justified?
So isotropic approximation meaning that
there is no angle dependency.
Frame,
there is no dependency of the cooling with the angle, with the direction of the particle. Actually, your diffusion equation is only energy, but you don't look at the angular distribution.
My assumption is that the configuration is isotropic in the source frame. So we have tangled magnetic field. So in principle, it should be the electrons are moving randomly in all directions. So I imagine that would be under this assumption, it will be justified. But I imagine, of course, the geometry of the magnetic field in the emitting region might be more complex. So, but okay.
I think for the magnetic field is not a big problem, but I'm more concerned with an isotropic inverse Compton cooling, because the external photon field can be very anisotropic. If you have a huge Lorentz factor, you have the aberration of the field.
But the synchrotron photon field in the case of BLX, so synchrotron emission field, is isotropic, as the electrons are
more or less, because the magnetic field is can be considered as
but if it's
more or less
for instance,
isotropic.
If it's
for the photon field.
If it's external photon field, then it might be very anisotropic. For the case of external Compton, when I considered interaction of the quiescent emission with electrons in the turbulent region, I fully admit that I took an average value. So I took an average energy density of the emitting blob, achieved it somewhere in the center of the turbulent region, and I didn't consider the anisotropy. And it's another thing to improve possibly, but that was something to start with.
Maybe it would be interesting to look at this factor. Okay, thanks. Then I had a few questions about your work on CTA and instrumentation. Also, it's not, I'm very far from an expert, but I was impressed by your work. I was just thinking of what is the importance of the PSF and the performance of the instrument, because we are not really looking for very, very high angular resolution. So how does it improve or degrade the performance of the instrument? What is the importance of this factor?
Yeah, so the Cherenkov light. So we want to achieve we want to achieve as smaller PSF as possible in order to have good resolution of as many pixels in the Cherenkov image as possible to as precisely characterize the parameters of the air shower in order to reconstruct energy more precisely and reconstruct arrival direction. So, and for the silicon PM cameras with 3mm pixels, so once you achieve 3mm PSF, you have very good resolution for Cherenkov images. So they're not kind of blurred, but they're more. You measure more precisely the light content and the shape and the background projection. So you really improve a lot when you get rid of the specular component. So when you mostly concentrate your light on the pixel rather than on the neighboring ones. So then you will have you actually if your light is entering in other pixels, so then you have a wrong estimate of the Cherenkov flux. So that's bad enough.
That's what was not obvious for me since the shower I set with an extended object. So do you win really a lot by improving the PSF? And sometimes it's even better if you don't want to saturate, for instance, the detectors. It may be better to spread the light on several detectors, no?
Well, the Cherenkov light pool is 100 meters. So ideally you want one telescope in the light pool for a single mode observations. For stereo vision, you want to sample the shower from many points. So anyway, you reach more accurate reconstruction of arrival direction with that, because as you more precisely know the orientation of the air shower, right, in monovision mode or with stereo vision mode. So there was a figure in my manuscript showing this technique. So when you have several showers and you have to cross the direction of them, and
Yes,
they
of course, yeah.
converge. So with smaller PSF, that will be much more accurate. So you can better at the end reduce your, subtract your cosmic ray background, for instance, and so you arrive at much more accurate flux measurements.
Okay, so my last question is, what do you expect CTA will bring most in the field of high-energy astrophysics compared to the current atmospheric telescope, Cherenkov telescopes? Of course, it will be more sensitive, but is it just a question of many more objects, many more observations? Will there be a breakthrough in the field, following your opinion?
So many well, it can address many important questions. So for instance, for blazar flares, on which I was working, so the CTA will be able to measure much finer variability. So the light curve time resolution will be much better. So you can really see the details of the variability pattern much better and understand the physical processes and better disentangle between different scenarios. So it's you see sensitivity. It actually not only for detection of more sources, but also for that. So it will detect boost number of AGN by 10 roughly. So you will see many more different objects, but also more precise measurement. Well, better spectral, better light curves for AGN. So you can really better understand the nature of the emission, and the hopefully with good angular resolution, with better resolution, spatial resolution. Hopefully we will be able to really understand where the gamma rays are producing, what's the geometry of the gamma ray emitting site, and I really hope for that, and that will be a crucial improvement. And of course,
Okay,
many
thank
more
you.
beyond blazars, there are many more scientific questions that CTA will be able to respond.
Yes, of course. Thank you very much. So
thank you, Gilles.
Yes, hello. So first, thanks for the great talk, and let me echo. Yeah, can you hear me?
Yes, absolutely.
Let me echo Paula's and Gilles' compliments and congratulations on a great thesis. It's really nice work you've done. So obviously you've had already a lot of questions, so I'm relatively short. Let me first come to 3C279. When you talk about that January 2018 flare, I'm looking at page 57 of your thesis now, figure 313. You only say that it's not significantly detected in this entire period, but I mean, Hess did release an ATEL on this January 28 for this one day. I'm trying to find the page now. So I don't think you showed this in your thesis. So I was wondering, does that mean that it actually was not significant? Did it go away, or what is with that single day flare on which Hess had put out an ATEL?
You're speaking about this particular night. Can you see my slide?
Yes, right.
So this is the secondary flare in Fermi. Yes, so I was involved in pre-flare, and during the pre-flare, especially at the, how to say, in the minimum flux, there was like 0.2 sigma or something. There was no detection at all, but our first two nights gave the contribution to this 3 sigma the most. So, and indeed for further nights there was a nice detection at, I don't remember, but it was like 7, 8 or even more. So it was significantly detected, and yeah, there was light curve like for these nights. The upper limits were deduced, while for beyond this band, so the flux measurements. What was your question exactly in relation to this flare?
Just wondering why you didn't even mention this one-day flare.
Didn't I?
Or did you? Maybe I just missed it.
Because I think I presented the light curve, the total light curve for this entire red band from the proceeding. So the one we published in ICRC with the task force. I think.
Okay, no, just glad to hear that it's
maybe I missed, but yeah, there indeed was detection for the very high energy flare.
Okay, very good. I'm glad it's still there, because one of her master students is working on interpretation for that, so it's
okay.
Nice if it's actually. So very good. Few questions on the model. Just first of all, the way you evaluate the radiation, is it including light travel time effects? I have the impression that you're essentially just using the emission at one point integrated over the entire region, and have that originating essentially from the center of your emission region, right?
Yeah, exactly. So I agree. So, but I think I checked at one point that these light travel effects were not that important. So I convolved with sort of kernel for including these light travel effects. So like slicing the blob, so that the size of the emitting region is around 10 to 16 centimeters, and so if we like. So part of the emission will arrive earlier than the center, and the closest point earlier, and the furthest point with the delay. But the overall widening of the light curve due to that, it was not really significant, because the variability is proceeding at 1 week scale, while this kind of effect is like the delays a few hours, so it's not really. We have 1 day resolution in the light curves, so at the end I concluded it was not worth to include that. So, but I think for larger emitting regions, that is, or for shorter variability, like 1 minute, 1 hour, to treat the intra-night variability, which we didn't try to. But for that, I agree that this is very important to include light travel effects.
Yes, right, exactly. Also, if you don't, then in principle you can produce variability on time scales shorter than the light crossing time scale. So, but it's good that you checked, so that is fine. Have you checked what's the magnetization of your emission region is? What's the ratio of energy densities in magnetic fields to particle energy density?
Yeah, that is. I didn't calculate, but I think. Yeah, I don't have a value in mind, but the ratio of the kinetic energy, the ratio of the magnetic, the b square over 8 pi by the. Yeah, I admit I don't have value in mind, but okay.
It's something one should check.
I think it's equipartition, so.
And it seems your magnetic field is way below equipartition, so that means your whole setup is strongly particle dominated. And then it's a big question if things
I agree,
like
it's contrary to the electromagnetically dominated jets, so.
Right, and then it's a big question whether acceleration mechanisms that are mediated by the magnetic field are still working.
Like magnetic, like Fermi 2.
Right, because you need the magnetic field effectively to do the work for the acceleration. But if the whole system is strongly particle dominated to begin with, then that might not work.
Yeah, I agree. So yeah, in my scenario, it was really the turbulent energy was injected, and the particles, the work on acceleration. So this energy was converted into particle acceleration, essentially. So, but I didn't really discuss the nature of I don't propose a concrete mechanism for generation of the turbulent energy, but yeah, I assume it's some transient phenomenon, one of those which I was showing in my slides, but I didn't really check the amount of energy that it can really supply the amount of energy necessary to generate this flare. So this is, I agree that this should be done at some point.
That's right. So I was wondering, I mean, you have discussed one very specific scenario for your one zone model, right? Essentially just switching on stronger stochastic acceleration. How confident can you be that there's not other parameter changes, maybe changes in the primary shock that might give you a harder particle spectrum or something, would not be able to give you a satisfactory fit?
You mean, yeah, if for instance, if the magnetic field is compressed and the emitting zone as well, and there is additional injection from shock. So you mean,
For example?
yeah, the idea was to stay within this. The idea was to stay within this assumption of weak perturbation, keep really the emitting zone unchanged, and consider like adding new additional free parameters step by step using well, not by within this approach, within this perturbation approach. The only way, if I understand well, you can do it only by adding another component. And my motivation was to because I cannot really predict whether this will help to overcome this issue with optical flux overproduction if I compress the emitting region. I'm not sure. And but I'm more sure that it is possible to do it if you have another component which is dominating the X-rays, and its optical variability is diluted by the emitting zone, the blob. So you can, in this case, I'm sure, intuitionally speaking, that I can have a modest flaring in optical, but very strong flaring in gamma ray and in X-ray. So, but for this configuration, yeah, it's not clear. And as I said, I decided to stay really within the weak perturbation assumption. So, and as I said, these where is these light curves? Yes. So as the flux during the flare is increased, so the pre-flare, post-flare flux are the same. So it's not clear how to treat the evolution of the, for instance, compression of the magnetic field and the emitting region self-consistently. Like, what is the time scale of returning back to the initial, or whether it will at all return to the initial value. So for me, it feels like a bit less natural than trying to add another emitting region.
Fair enough. Very good. Yeah, I think that's almost it. Maybe one tricky question. So you have Compton cooling that actually includes Kleine-Schiene effects as well, right? So
that's
at
true.
The highest energies, you do have Compton scattering in the Kleine-Schiene regime. Do you maybe see a problem then with treating the electron evolution with the Fokker-Planck equation?
Sorry, can you rephrase? I didn't get it. So what's the problem actually with Kleine-Schiene effects?
Yes, but that's my question. If you're aware of any potential problem then treating the electron evolution with the Fokker-Planck equation?
Well, at each time step, I estimate the synchrotron energy density, and this is done at each time step, and that I compute it with the electron spectrum from the previous time step. So for a fine grid enough, I don't really mistake a lot with the estimation of this effect, I guess. But
well, no, that's actually not what I'm getting at. If you look at the derivation of the Fokker-Planck equation, it is based on the assumption that every individual interaction changes the particle energy only by a small relative amount. Right? So delta gamma.
Yeah, in Kleine-Schiene it's not the case. So the electron gives almost entire energy to the photon.
Exactly. So strictly speaking, the underlying assumptions to derive the Fokker-Planck equation are then no longer valid.
So there should be another term added taking it. So another term like non-linear terms included, something like this?
Yes, I mean, to be honest, all my codes do exactly the same thing as you do. So, but strictly speaking, yes, if you want to do it exactly right, I believe actually Andreas and his group have done that in one of their codes. In principle, if you are at the highest energies, you have to kind of do a transfer. That's for every Klein-Machine interaction, you transfer the electrons immediately to the lowest energies and not differentially in energy.
Okay, I have to admit I was not aware of this issue, but yeah, thanks for elucidating that.
At least something that one should be aware of. As I said, I'm doing the same thing. So.
That was useful.
Good. All right, that's all I had. Thank you again.
Thank you, Marcus.
Yes, I'm here. Anton, thank you for your good job in report. But the better the job is, more question we can ask you. I will start from simple question. Please, page 35.
Yeah, I can. Yeah, finally. Sorry, 35, right?
35. Some Bethe-Heitler cross-section. Please change that is not nucleus atomic number, but is the charge of.
You're talking about the manuscript.
I have only your manuscript. Maybe you correct that. Yes. Well, okay. Equation 2.9.
2.9. Oh wow, where is that? 2.9. Yes.
You write. You wrote f is integral from I with dv d nu, так сказати. A flux is integral from intensity, but this is not correct. That integral is the same intensity, but not differential one, but only total intensity. Now, what's that value? You see that f is not, here must be intensity, not f. F is integral from intensity along of the light of sine, this cosinus theta. Well, let's go to page 8.
Page?
8. 8. This.
What I'm doing, 8.
You divide flat spectrum and steep spectrum with alpha equal 0.5. Yes? You see.
I mean, can you repeat the number of the page? Because I'm not sure.
8.
Yeah, but in the slides or in the manuscript, because in the manuscript is just description of the.
Yeah, I remember you. The boundary between flat and steep spectrum is spectral index alpha 0.5. The question, why just 0.5?
Well, I think that what conventionally is, you have to divide somewhere. So that's the way to, like that's a threshold. I was not the one who chose that. It's typically in the community what is.
Well, if you synchrotron spectrum, the flux is proportional to frequency with power with spectral index alpha. Right? Such alpha is connected with spectral index of cosmic ray electron. And spectral index of cosmic ray electron is typical 2. Therefore, alpha is gamma minus 1 divided in 2 is 0.5. This question is, for 3 different spectral index use the same letter alpha. Spectral index alpha, photon index alpha is called alpha tag, and in spectrum is the same spectral index alpha. It's different spectral indexes.
I attach different subscripts in order to avoid this confusion. So
no, maybe well.
R or.
Please show the figure 5.3 about magnetic reconnection.
Okay. So yes, I will. We're almost there. Yeah, so here we are.
5.3. Please explain the magnetic field line just right in this position.
Sorry, what is your question exactly?
Correct. Is such magnetic field leading just in the opposite direction should be.
You mean these arrow, but I mean
last magnetic field line just lies from the right part has wrong direction here. Because such line must be like to such another line, go from left to right. And here after reconnection, we must go from left to right here.
Okay. Well, I didn't notice that, so I took it from a review and okay.
Well, now the serious question. Can you find the equation 6.1 one zone model?
Can you repeat the equation?
6.1 physical modeling of Markarian 421.
Okay, equation 6.1.
Equation 6.1.
Almost. Where is it? Where is it? Yeah. Oh my God. Yes, here we are. This is what I'm injecting in the emitting region.
Yes, but you wrote, I inject cosmic rays on the shock front, and such cosmic rays penetrate inside bubble.
Not cosmic rays, but electrons.
No, electrons is cosmic rays. It's the same. High energy particle.
Yeah. Okay. Yeah.
Well, electron. But if you look in 6.1, your injection function doesn't depend of spatial coordinate. It depends on the energetic coordinate. As it means in your kinetic equation, you inject your particle simultaneously, uniformly inside your bubble. Do you agree? From a mathematical point of view.
This is the number of particles which is entering the volume of the entire emitting region per unit of Lorentz factors per unit of time.
But such number of particles is injected in each centimeter cubic in your volume of bubble.
Yeah, it's not. I mean, of course, it's not. It is more complex than that. It can be inhomogeneous. It should be inhomogeneous.
Yeah, you like have your kinetic equation. Your kinetic equation doesn't depend of coordinate. It means that you must
homogeneity. Yeah.
Well, if you inject such particle in uniformly, the time of the escaping due to the diffusion process inside bubble is larger than your time escape radius of bubble dividing on C. They will diffuse in magnetic field because his thermal radius is smaller than radius of bubble. In the diffusion time escape will be higher than simple time escape radius of bubble dividing the velocity of light. You can, you know the energy of electron, you know the value of magnetic field, you can calculate thermal radius. It means that your
typically very small, yeah.
Yeah, it means that your electrons will live more longer in your bubble. It means they will radiate more effectively, and maybe as a result, you will not need so large Doppler factor as you have above 30.
No, but in fact, it's more depending on the general configuration of the magnetic field because like the particles are attached to magnetic field lines. So
if your electron will be live longer inside,
just crossing it in 1 hour. No, I mean, it doesn't matter that it is.
If your
it's just treating on magnetic field lines. So it's not really diffusion. If I don't have turbulence, then it's not quite diffusion. It's just
it will be diffusion because its thermal radius very small. It will be diffusion from the center, from the internal of bubble to the edge of bubble. Next problem, question problem. Your shock wave will be ultra-relativistic because Doppler factor of bubble is very high. Acceleration of electrons, not electrons and the ultra-relativistic shock wave is enough complicated problem. I, for future, would like to you pay attention with this situation. The magnetic field is perpendicular. Is a lot of problem with acceleration of electron component of cosmic ray at the ultra-relativistic shock wave. The magnetic field can play an important role. Well,
okay. I agree that this was clearly a simplification.
What is interesting in your model? In your model, such shock in your model is really analog of Bow shock around the pulsar wild nebula, around of shock when you have ejecta of supernova remnant in interstellar medium. In this case, your plasma will flow around the bubble and it will be advected downstream. It means that your cosmic ray will have time for acceleration, something not very long, because such time of acceleration will be equivalent to the time of leaving such plasma just around your bubble.
Okay.
Another problem. You estimate that the thickness of such post-shock region between shock and bubble is some 10 to -4 of radius of bubble.
Right.
From the geometrical reason, if you have the plasma flow around the blob, you can have such very thin thickness of post-shock region. So from the,
it was one of the attempts to estimate. Actually, it was not favored because I assumed that the cutoff is not due to the cooling or escape, but the cutoff is due to the inefficient shock acceleration.
Purely hydrodynamic, my data hydrodynamic. The thickness of such, the distance between shock and bubble must be of order of radius of bubble. Maybe 1%, but not to 10 to -4. No, it needs the best to more correct estimate.
Yeah, it was just exploration rather than, we don't claim anything in this case, so it's just a discussion.
And some proposition for future. What in your screen, you have such typical picture. We have bubble, we have shock around bubble. In real, more realistic picture, such bubble drives the shock in the plasma of jet. It's both shock. In the same time, the reverse shock arises in the bubble, and inside bubble, we will have reverse shock. It means that your two-zone model will be, you will have gratis, free of charge in this model. More realistic model give you just two zone, more correctly does 3 zone. Is the post-shock zone from post-shock region from the bow shock? It will be post-shock region from the reverse shock. It will be the left non-disturbed bubble. I think that such really hydrodynamic model will be just realistic model of your turbulence. You don't need put turbulence by hand. You have here such two shock, bow shock and reverse shock. A reverse shock will generate turbulence very effectively, and you can calculate very simple but effective realistic model with two shock, with bow shock and with reverse shock inside the bubble.
I see.
And another accent proposition. You consider only synchrotron self-compton. You are working enough the large distance from the center from the black hole. Your radius of bubble is 10 to 16. It means the jet is from center is distant also 10 to 16. My question is, if you calculate the contribution of typical iris Compton, external component, with CMB, infrared, optical, and background photon, in some time you must go from domination of CC synchrotron self-Compton effect to the inverse Compton effect. Can you estimate where at such distance in your model you will have such transition? Maybe such transition will help you to explain the experimental data. But at a very large distance from the center, of course, your synchrotron self-Compton will be weak and will be dominate external Compton. Maybe in your region just will be such transition from domination of synchrotron self-Compton to the domination of effect of that typical external inverse Compton emission.
Yeah, in the case of BLAC objects, that's the external Compton typically negligible. But in case of LBL, low frequency peak BLAC, the extended jet might contribute to the external.
But it depends of concrete value of parameter, yes? At concrete value of parameter. You work with more great distance, 10 to 16, 10 to 17 centimeter is not typical from BLAC distance. We expect synchrotron self-Compton, yes.
The emitting zone is further. It's up to 1 parsec away from the black hole, like 0.1 or 1. It's much larger than the size of the blob, typically by a factor of 10,000 or something. So it's compared to the size of the blob, that's pretty far.
That's all my question. Dan, thank you for answer.
Thank you.
Thank you. I think, yes, we're done with. Okay, myself, I'm not an expert in this field, but I have also some yes. So something that is a little bit puzzle for me is you propose the selection for Markarian for 21, the selection of a specific flare. And but I was wondering, you discussed in your manuscript about why you choose this one, but I'm a bit wondering, I mean, because so you have the sampling of the some light curve. Is it the best example that has been obtained for all source? I mean, observed for any energy? Because I'm surprised, I mean, by the statistic that is not that great. I think it depends on the wavelength, of course. But
I see.
I mean, is it the best we can get up to now? I mean, why do you choose
it depends on the band really heavily, because the strategy of Cherenkov telescopes is very drastically different from other. For instance, Fermi-LAT, the GV gamma ray band instrument it operates, it has a very wide field of view, so it can see many sources, and you can have good time resolution, and especially now when the IRFs were improved, so you can have even at lower energies. Which is not the case for Cherenkov telescopes. So typically they have narrow fields of view around 5 dB. So they often miss the peak of the flare, and they like the Fermi or X-ray instruments issue alerts, and so the Cherenkov telescopes point, and then it might be late. So then it might post flare measurements already, and the particularity is that the sensitivity of instruments is very much different because it's different detection technique. So you've got completely different sensitivity and hence the different time resolution. So for Cherenkov telescopes, the time resolution heavily depends on the level of flux. For PKS 2155 is one of the BLAC objects. During its 2006 flare, the measurements, the light curve, it was like the variability was measured after a few minutes, I think, and show flares of Markarian 41 were also detected down to 3 minutes. So it's, but in order to have like 3-minute bins on the light curve, you have to have good photon statistics. So, and what does it mean have good photon statistics? You need to have signal. You need to have enough photons. So you need to have like high flux. And these, as you can see for this flare, it was not the case. So during the peak, there was no really good measurement by Veritas, Hess, or Magic. They missed the peak. So, and only small telescopes like Tactic and Hagar, which are Indian Cherenkov telescopes measuring. So they have a really quite small collecting area, and they really cannot, and they don't claim perfect calibration also. So they have no way in measuring during level of 20 crab. Maybe they don't they cannot reach better than half a day
Yeah,
or
but
1 day.
even I think in the manuscript, I mean, the coverage optical also is not that extreme. I mean, I'm just really wondering if it's not a question of organization of the community in terms of reacting.
You need to coordinate, yes.
Because you see that in, for example, some community like the gamma reverse community, they know how to do that quickly. So I'm wondering, I mean, if you can get much better data by adding a little bit more organized community, in terms of multi-wavelength.
That would be great, because coordinate 10 or order of 10 instruments for a specific flare. It's I think it's an effort to.
Yeah, but people do it now in many fields. So
I agree. Yes. So hopefully in CTA era that would be the case.
I think it would be important. And first, excuse me, I should have started with congratulating you for the huge body of work that you have done, and something that I think that has not been highlighted yet. I think you have been very honest in the way to say that things you have done in the manuscript, things that have been done in the task force. Not on that, that's something that is appreciated in the work, and also the fact that you touch many different aspects. I mean, like data analysis, theory, and instrumentation.
Maybe I can show. Maybe I can show you. Like, does the people see you?
Okay. Don't worry. I mean,
yeah.
Okay, I can go. They have seen me before. So.
Okay.
Something also that is that was not clear to me. You discuss it a bit in manuscript. It's the state of the art in terms of what is done in terms of modeling. Why? I mean, you propose a specific configuration. I think it's Gilles asked you or Marcus. I don't remember who asked this question, but why? I mean, you answer why you choose a specific model. But what is the state of the art in terms of what people do in this field of modeling short variability? I mean,
okay.
It's maybe very large question, but
I agree that so the activities are people try to explore different scenarios, and not only as I showed it during the introduction. So it's not only microscopic properties of the emitting zone, but people explore many more. Like in our group, for instance, there is a postdoc who is exploring ablation of a gas cloud entering the jet. So that's a completely different type of model for variability. And people propose various mechanisms and for flares. And this is the idea, to try all this variety and find what works and what doesn't work. And then with more observational constraints, hopefully in the future with CTA as well, some models will be ruled out, there will be new models, sure. And many more constraints will tighten they will have to understand better the nature of the flares. So the idea is to find recent models which work and try to improve them, add another component. So at the moment is more or less something like this, but you need really multi-wavelength observations, so from radio to gamma ray, and that's how you can better constrain models. For instance, some, like you see, without optical measurements, I wouldn't be able probably to exclude one's own models. So to have concluded, okay, the simplest model works, and so you need really a good coverage across electromagnetic spectrum. And of course, you also want to go beyond. So you want a multi-messenger approach. So neutrino would be really great. Measure neutrino fluxes. That will be constraining for hadronic models a lot, as hadronic interactions initiate neutrino production. So the more coverage across electromagnetic spectrum, and with more sensitive instruments, so you can better understand what's happening during this mysterious phenomena.
Okay.
So I hope that answers.
Okay. If you go to slide number 30.
30?
30, yes. Yeah. Just I could take this one, or 32 is the same. So you have this blue region. I mean, that is region at the origin of most of the emissions, right?
Yeah, in the low
But
state.
I'm a bit wondering. I mean, so this one is sitting in the middle of what we call this cone, which is a jet. And so,
Yes.
but this jet is, what is this normal jet doing? So in terms of emissions.
So maybe I didn't emphasize that properly, but the emitting zone, the blob, is like a plasma condensation. So the magnetic field is orders of magnitude higher than in the large-scale jet, and the density of particles is much higher, and the magnetic field is tangled. And so due to this fact, so as you have higher densities, pretty much everything, so you have emission that is dominating. And in the jet, the magnetic field is lower, so you have lower intensity, and you have, of course, lower frequencies. So large-scale jet is mainly emitting at lower frequencies, like radio in the radio band. And in this plot, so if we believe that we describe the, well, if the emission starting from 10 to minus 3 eV, which is if 1 eV is optical, so that's 10 to minus 3 EV would be, well, 10 to 15 minus 3. So that would be 10 to 12 hertz. So above 10 to 12 hertz is dominated by the emitting region. And what is below 10 to 12, terahertz, so that will be dominated by the large-scale jet. And but there are authors that argue that the extended jet might provide contribution even up to the optical band. I mean, non-negligible contribution extending up to even 1 eV energies. So the jet is radiating, but at lower frequencies mainly.
Okay. And do you think there is anything to learn from, because there is a community where you have high energy emission from jets and accretion flow, and the X-ray binaries? Do you think there is anything to learn from what has been collected on some time scale and variability in the observation of the X-ray binaries?
Yeah, I agree, because I mean, they also, if I remember well, they also produce jets, but at much smaller case, is the right? So like micro quasars, and so it's useful knowledge. So you have, they share. I'm not an expert on that, but I believe they share some similarities. So some of the it can provide an input, definitely. Well, I'm not sure it's as broadband, like it's okay.
You have so that
Gamma rays,
Fermi, you have but you also have
soft gamma rays. Okay.
You have even with Fermi. So
okay.
And you have so that jet pointing towards the observer, so with high Lorentz.
So maybe for the jet structure, but you see the mechanism. I think the mechanisms for jet launching are not exactly the same as in AGN, and I mean, in any case, energy scale is completely different. Yeah. But well, there should be some similarities. Well, the radiation mechanisms, possibly. The presence of relativistic particles, and the interaction with the quantum fields. Mm-hmm. So that should be useful. Okay. But did it because the question you were asking was mainly, what is the analogy between the?
No, I think for you, is there anything to learn by comparing with what has been obtained with the X-ray binary, where you have a lot of study on short time scale with multi-wavelength, with SOD, you have a lot of. You don't have this double peak structure, at least not in the same way. So.
Okay. Yes, well, it's useful to talk to other communities always. So.
And final question. So, do you know why the ASTRI telescope was chosen the solution? Why this solution has been chosen regarding GCT? So.
It's a very good question, and I'm really thinking. I have to think through how to answer it properly, because
I'm not taking a popular view of the
In
political
fact, it
question.
was. It was like. It seems to be that it was like more political decision rather than like justified, because okay, they have good design, of course, and no one is objecting that. I mean, but apparently, well, that was the decision by CTA consortium. They proposed initially to merge or harmonize the three designs, but that's very difficult because you got single dish telescope and two double dish. So I don't know, that is not feasible. I think that was because Italians, they provide more funding, so they have more funding available, and that because they can build things readily. So the decision of the consortium was to give them an opportunity. As for French English side, it was more complicated. Okay. So, but in principle, I mean, Astro is a very good design, but the structure of GCT and the PSF seems to be better. And but it's not clear because the idea was also somehow to learn something from GCT, so implement things from what the advantages of GCT to Astro, but somehow they're not willing to, the Astro community, they're not willing to really change their design. It's an issue which is not yet resolved, so we will see. So yeah.
Okay,
Thanks for your questions. Yeah.
Yeah, thank you. Okay. So now I will ask if, for example, Hélène, you have questions. Yeah, it's okay if you come here because of the microphone.
Okay, so in fact, I do not have any question to Anton because I think we already discussed quite a lot. So I would like to say that I really appreciate very much to work with him because, okay, he has great skills in physics and in computing science. So this was extremely useful and very important. And also he has a great motivation and always a real enthusiasm towards research, which was really very important, especially this year with all the troubles we had with the sanitary crisis, and it just went on and succeeded to make to provide a huge work despite this difficult condition, even until the very end, and even a few weeks before the defense, we had a new situation in France again. So really, congratulations to you, Anton, for having done all that despite these difficulties, and I wish you all the best for your future in scientific research. So, yes.
Thank you very much, Hélène. Thanks.
That's the same thing. I think I don't have any questions, so because we also discussed a lot already. And I was also wanted to say also that I really enjoyed very much working with you for the last 2 years. This year, of course, was really horrible for everybody. So I really, I think you have all my respect for having managed to get work done during this year, which was really difficult. And you got to your thesis, which is really a very good piece of work, I think. I also think that you did really a great job, especially on the modeling part, where you really took into hands the description of the turbulence, which I find quite consistent. And this was really went beyond that, what we did, what we set out to do in the beginning. So we really went a bit further actually than what we thought. And I think it's really nice. It's a nice model. It's a nice coherent one-zone model. So I thought, I think you really brought quite a lot of good humor and fresh ideas into our lab, and I hope that we will continue to work also in the future together.
Thank you, Andreas.
Thank you.
I was happy to hear that.
Okay. Is there any question in the audience? Online? People want to ask something online? No? Okay, so now, so the jury is here. So we have someone get managed so that people you go to the waiting room. Yeah.
So for me, I stopped the my screen sharing and
On reste ici, c'est ça?
Oui, on va se mettre là.
Oui.
Okay. So I will put everybody in the waiting room. People who are not in the jury. The jury members should stay, of course.
Yes. So I cannot stop my. I cannot. Okay. Can you put me in the waiting room as well, because I cannot switch off my.
Sorry, what is happening now?
My microphone. Okay, yeah.
So I go out, right?
Yes.
Yes.
Thing is, there are quite a few people connected.
That is also not bad.
Donc, tu devras réadmettre tout le monde après à la fin.
Ouais. Ceux qui sont encore là. Je pense que je vais faire ça.
Les gens ne peuvent pas se mettre individuellement en waiting room.
Je pense pas, non. Je pense pas que tu peux le mettre tout seul.
Okay.
Je suis pas sûr. Ah, mince.
T'as mis qui en waiting room? Ah oui, Gino.
Shit. It's changing too quickly. Non, c'est bon.
Il y a, ça, c'est qui est en dessous, le caractère un peu cyrillique là.
Ok, so Mathieu, tu te déconnectes du coup? Ok.
Donc, par contre, il manque